Okay, so let's go ahead and read our hypothesis test question. In 2002, the mean age of a death row inmate was 40.7 years old. The sociologist wondered whether the mean age has changed since then. She randomly selects 32 death row inmates and finds their mean age is 38.9 with a standard deviation of 9.6. What can you conclude at the 5% significance level? So let's go through and find our key terms here. First of all, this is changed, so it's not equal to. First of all, we're wondering if it's changed, so it's not equal to, and if it's changed from 40.7 years old. So the 32 is the N, the X bar is 38.9, S is 9.6, and alpha is 5%. Let's set up the null and the alternative hypothesis. The null hypothesis is the mean hasn't changed. In other words, the mean is equal to 40.7. The alternative is it's not equal to 40.7. It's changed. This is a t distribution. We have not been given the population standard deviation or sigma. So let's set up our t distribution here. This is our distribution of all possible samples of size 32, the mean age of death row inmates. We'll do 0, 1, and negative 1 standard deviations from the mean. The mean of all of the means is assumed to be the null hypothesis, which is 40.7. Assume the null to be true. The standard deviation, or the standard error of the mean, is s over the square root of n, in this case 9.6 over the square root of 32. This gives us 1.7. So one standard deviation from the mean gives us the following. All right, we want to know where 38.9 lies. How unusual was it to get a mean age of 38.9 if the true mean were 40.7? Let's find the test statistic. So the t statistic is x bar minus mu over s over the square root of n. In this case, we have 38.9 minus 40.7 divided by 1.7 approximately, negative 0.06. That's our test statistic. We want to compare our test statistic to our critical value. In other words, what's our cutoff? Was that unusual? So we want to find our critical values, and that comes from alpha, or our significance level. And so alpha is 5% in this case, and we have a two-tailed test. That means I have 95% in the middle, and I have 5% over 2, or 2.5% in each tail. All right, so if I want to find that critical value, I can either use a t-table, or I will use inverse t. It's 0.025 area to the left, and the degrees of freedom is 31. That gives us a critical value of negative 0.204. That's to the left of our test statistic. So by the way, this is a two-tailed test, so it's plus or minus 2.04. Therefore, we are going to fail to reject the null. Our test statistic does not fall in our critical region. If I fail to reject the null, that means that there is insufficient evidence to show that the mean age of death row inmates has changed. All right, so we've made our conclusion just with our critical values in this case in our test statistic, but I want to also show you the p-value method. So the p-value we're comparing to alpha to say, is this unusual? Remember, alpha was 5%, so that's 0.025 in each tail. All right, so we want to know our p-value. Our p-value is 2 times the area to the left of our test statistic is negative 1.06. So one way, and I'm going to do the area to the left of that test statistic times 2. I can do the t-CDF function, which is basically a t calculator. That gives us the area to the left of that t-value is 0.149. Multiply that times 2. I get a p-value of 0.298. So if I want to not have so much rounding and get a more accurate value, I can do a t-test. The t-test, I'm going to use stats. Our null is 40.7, sample mean 38.9, 38.9, sample standard deviation 9.6, sample size 32, and we're looking for a two-tailed test. We get to 0.297. Again, it's just slightly different because of rounding, and that is we're going to fail to reject the null. That's because our p-value is 0.297. That's greater than alpha. That is not unusual. 30% almost of the cases would come out this way, and therefore we're not saying that's unusual, and we can't show that there's enough evidence to show that the mean age has changed. All right, let's go ahead and do a second example, this time with data. Here we want basically a manager for a fast food restaurant has changed the methods for the a new system for the drive-through, and they want to see that if the average time has decreased. The old time was 92.1 seconds and on average, and so we want to see if he's decreased the time. So he randomly selects 10 customers and records the wait times. Okay, so information here we have, if it's decreased, that's a left-tailed test. We want to see if it's less than 92.1. We have n equals 10 for our sample size, and our sample mean and our sample standard deviation have to come from our data. And I plug that into my list, into my calculator, or into Excel, or to wherever you're going to get X bar and sample standard deviation. You get the mean time for the sample was 84.56 seconds, and the standard deviation 18.77. Let's set up the null and the alternative hypothesis. The null is the mean time hasn't changed. It's still equal to 92.1. The alternative is it's less. It's decreased. This is a t-test. We were not given sigma. We're not given the population standard deviation. So let's go ahead and draw our curve. By the way, we have to assume that this data has been checked for normality. The n is not greater than 30, and so I should have built into the problem that you actually check for normality. We're going to go ahead and skip that step here, but check that you have normal distribution for n equals 10, and you can still use the t-curve here. So I'm going to draw the curve, put one standard deviation away from the mean. The mean is 92.1, and the standard, because the mean, by the way, is the null. You're assuming the null is true, 92.1 seconds. The standard error is s over the square root of n, which is 18.77 over the square root of 10. In this case, 5.94. So there's one standard deviation away from the mean. We want to see how far the new mean is from the old mean. So the new mean is 84.56. What is our test statistic? Is that unusual? It is less than our old mean, but is it significantly less? Is it statistically significant? So let's find our test statistic, which is our t-value. T equals x bar minus mu over s over the square root of n, which in this case is negative 1.27. So that's our test statistic, negative 1.27. I want to find the critical values. The critical value comes from alpha. In this case, alpha is 10%. So I'm going to have, and this is a left tail test, so I have the entire 10% in the left tail, 90% to the right. I could find the critical value either from the t-table or by using my calculator and doing inverse t. Area left is 10%, and the degrees of freedom is 9, 10 minus 1. So the critical value is 1.38. Again, this test statistic does not fall in the critical region, therefore I fail to reject the null. If I fail to reject the null, my conclusion is that I do not have significant evidence. In other words, there is insufficient evidence to show that the mean wait time has decreased. There was not statistically significant evidence here, and therefore he could have just possibly gotten a sample that was slightly smaller than what they had before, which was the 92.1. Let's look at the p-value method. We're comparing the p-value to 10%, which is alpha. So this is a left-tailed test, 10% alpha is in the left. We want to look to the area to the left of our test statistic. 1 times the area for a left-tailed test, and our test statistic was negative 1.27. One way we can do this is using a t-calculator and figuring out that the area to the left of negative 1.27 is 0.118. A better way to do this on your calculator is a t-test. The t-test, you're going to use stats, you don't use stats. You're going to use data.